Well, we're moving on here to our next section, which is potential applications. And our first speaker isn't. Am I in the mic? There we are. You got to get really close. All right, our first speaker is Tamuka Magadzire. He represents the Famine Early Warning Systems Network. And I see him on our screen here. So again, this is the potential applications section.
Thank you very much, colleagues. I'll start with this statement that the El Nino-induced drought that affected Southern Africa between 2015 and 2016 was one of the driest such periods in at least 35 years. It caused a drop in cereal production of over 10% compared to average harvests, with widespread crop failure in 4 countries, as indicated by the red areas in the map or that you see before you. As a result, 23 million people were in need of emergency assistance by the end of the rainfall season, and an estimated $2.7 billion was needed to deal with the emergency. Yet, despite the severity of the impacts, a disaster was averted, in part due to early warning, including rainfall forecasts that accurately predicted the dry conditions months ahead of the event, as well as monitoring and a quick response by government and humanitarian agencies. Good afternoon, colleagues. I'm going to be sharing with you today how we believe that multi-year prediction can aid planning for drought impacts on food security. We wrote the abstract for this paper in collaboration with my colleague, Jim Verdon, who is from USAID, who is in the meeting with us, and would like to acknowledge the great work being done by colleagues at FuseNet, USAID, University of California, NOAA, USGS, and many others who have made this work possible. Allow me to start this talk by introducing you to the Famine Early Warning System Network, or FuseNet, which is a leading provider of early warning and analysis on food insecurity since 1985. It's funded by USAID, and FuseNet's goal is to provide objective, evidence-based analysis to help government decision makers and relief agencies to plan for and respond to humanitarian crises. It covers close to 40 countries in Africa, Central America, and the Caribbean, as well as Central Asia. And we regularly produce projections of food security that look out 8 months into the future, as shown by the map you can see before you here, indicating different levels of food insecurity in the near term and the medium term. But why FuseNet, especially for this talk? Well, FuseNet uses a multidisciplinary approach to incorporate different aspects of food security into early warning. These aspects include agroclimatology, livelihoods, and markets and trade, and nutrition, which I can call the 4 elements listed up here. Climatology is, of course, of particular interest to many of the participants in this forum, and its importance to food security would probably be due to the fact that 80% of the world's agriculture is rain-fed. These 4 elements that I've mentioned here do provide different lines of evidence that are subjected to an elaborate early warning analysis that results in food security projections that can look ahead up to 8 months. The aspect of scenario development, which is highlighted here, is an important entry point for agroclimatology. The scenario development process that I mentioned can be broken down into 8 steps as shown on this slide. And they allow an analyst to use a set of available data to systematically come up with a projection or a scenario of what the food security is most likely to look like in, say, 3 to 6 months. This scenario would be highlighted by step 7 here in red. And one of the main inputs in this process from the climate perspective is step 3, highlighted in purple here, which is develop key assumptions. So for a rain-fed dependent area, for example, then, an important key assumption could be rainfall in the upcoming March to May season will be below normal. So after the scenario development exercise is complete, as described above, we end up with a number of outputs, of which I'll just focus on the Food Assistance Outlook Brief, or FAOB. We see here that it was developed in March 2016, and the projected food assistance went out through to September 2016. And I've also highlighted the statement here for Malawi, which shows the August 2016 to March 2017 was then being focused in terms of the food security outcomes for that period, which is a period some 13 months from the time that the FAOB was developed. USAID then uses the information from the FuseNet Outlook projections to help with decision support for food assistance. Different types of food assistance are considered, for example, local procurement of food, food vouchers, and the like, depending on the conditions on the ground, and also in an effort to avoid disrupting markets, the most appropriate response is provided. Other interventions that assist in resilience building are also provided as appropriate, and one of these will highlight them later. But now I just want to switch to an example which shows how early warnings and food security projections are being used to help avert famine. You know, in July to September 2015, Ethiopia experienced a drought similar to the 1984 drought, as shown by these two maps. 1984 on the left, 2015 on the right there. As you may be aware, the 1984 drought in Ethiopia was severe, leading to crop failure and major livestock losses. Hundreds of thousands of people died in the ensuing famine. But in 2016, things were quite different. In February 2016, as shown on the map on the left, FuseNet projected food insecurity conditions, which were classified as emergency for the June to September period, assuming that no humanitarian assistance would be provided. But this very early warning then developed due to effective climate, early warning, and decision support services, allowed for a good response for 12 million people, such that by the start of the June to September period, as shown on the map on the right, the projections were now indicating much lower levels of food insecurity, thanks to the humanitarian assistance that was now in the pipeline due to the warnings that had been provided. Now, we're already using climate projections for preparing food security outlooks. The map that you see shows the probability of precipitation being above or below normal in the January to March period, which is part of the main growing period in Southern Africa during El Niño and in different parts of the world. Now, given that we've got a good long lead predictability of ENSO, I think earlier presentations in this session talk to that in this workshop. This means, therefore, that it gives us the ability to make 9-month projections when forecasts are indicating confidence for a positive or a negative ENSO event. Now, the possibility of even longer lead ENSO forecast, as is was discussed in this forum, is of course exciting for us, as this allows the possibility of even longer lead food security outlooks. Now, along with rainfall, we also have a number of other agroclimatic indicators that we help us to quantify the quality of the season from an agricultural and food security perspective. One of these indicators is the Water Requirement Satisfaction Index. Now, the WRSI, for short, is a crop-specific water balance model that is calculated as a ratio of the actual evapotranspiration from the cropped area. It's a ratio to the water requirement or the demand. So it's basically a supply to demand ratio. And so an index of 100% means that the crop has met all its needs. Now, in the above three maps that you see, in the three maps that you see before you there, we see 3 consecutive seasons from 2016 to 2019. The first of these seasons was very good, and they got progressively worse as the from 2017 through to 2018, 2019. Now, you can imagine the implications for planning if we could have known by, say, 2015 that we would have 1 very good year followed by 2 bad years. Now, just hold that thought, and we'll get back to that shortly as we examine what actually happened on a longer-term series. And we find that actually the WRSI tracks food insecurity very well. It's actually being used to provide crop insurance as an index for crop insurance. And in this example, though, we want to see how 2015-16 and 2018-19 were actually quite bad years. And we noticed that the food insecure population was actually its highest at its peak in these 2 years, which also showed up as very bad in the WRSI. We see spikes of close to 10 million people in both 2015-16 and 2018-19 due to the droughts that occurred there. Right, now we get back to looking at the 2015-16 drought, and we track the process from the forecasting through to the food security and the drought response. We note that by July 2015, NOAA CPC had already issued a strong confidence for El Nino during the 2015-16 season. And of course, El Nino is associated with below normal rainfall in Southern Africa. By September, the NMME, or North American Multimodal Ensemble, as shown in the middle panel, was already projecting below normal rainfall in the November to January period. And when we look at the October to February rainfall, it turned out to be among the lowest in over 35 years in many areas, as shown by the brown colors shown in the map there. Looking on to now the response, you've already seen these numbers from the first slide that I shared with you, but the number you had not seen is that USAID provided $331 million, about 12% of the estimated response required. And we're going to take a look at the breakdown of these numbers. We noticed that about $278 million, or 82% of USAID's response, was channeled towards providing food, which was an immediate need given the scale of the harvest reductions. Now, despite the severity of the emergency, 15% of the response was still included interventions directed at agriculture and food security, which is a longer-term outlook. Now, these agriculture and food security responses, as defined by USAID, include interventions that increase livelihood opportunities, that increase community resilience to shocks, and support agricultural infrastructure rehabilitation, among others. We can explore how these type of interventions could be expanded if we knew with some confidence how the next couple of seasons would pan out. Now, this is an example, again, back to now moving on to 2017-18 to 2018-19, we see that we had two poor seasons in a row in some areas. This is what's indicated by the orange colors there. The question that arises now is, what actions could have been taken for food security planning if we knew in advance that two poor seasons in a row were coming? Perhaps for this, in the area of humanitarian assistance, considerations could include repositioning of stocks, for example, as more food stocks would be required than for 2 years in a row than if only 1 year was projected. And of course, this could also in turn lead to improved logistics planning. In terms of, we also can see how this multi-year prediction could also improve the application of ongoing initiatives, such as the USAID Feed the Future Southern Africa Seed Trade Project, which is mentioned on this slide. This project by USAID is aiming to improve access to and trade of high-quality seeds in Southern Africa. Now, given a scenario of a 2-year forecast, the first year, for example, could be used to increase production and provide distribution of the most appropriate seed varieties to relevant areas, whether these are high-yielding seed varieties to maximize production in a good year, shown in by the green there area, or it could be promotion of drought-tolerant varieties to minimize losses given a forecast for a poor second year. It's very difficult to produce the seed needed for this upcoming season. So this multi-year prediction then does allow some room for production of seed as well as distribution of that seed. But what of a situation
2 minutes
where
remaining.
Okay,
2 minutes remaining.
Thank you. Okay, thank you. We have a situation in which a number of bad years, such as what happened in 2014-15, then we know that we could actually include to our list of interventions there promoting alternative livelihoods, knowing that the bad years are with us for some time. We have a number of drought mitigations that can occur in addition to this. This can include development of preparedness plans, water conservation programs, crop insurance, and so on. We have also a number of opportunities and challenges that are related to the production side of the food security, given the long lead forecasts. We know that already farmers have a tendency to use drought-tolerant varieties when they know that the seasonal forecasts are expecting such. But on the other hand, there's limited access to some of these forecasts, and the reliability can also be an issue where confidence is knocked down when the forecasts are not don't turn out as expected. Additionally, subseasonal rainfall distribution is also important for things like dry spells, in the instance whereby you get a good seasonal totals, which are normally what are predicted in the forecast, whereas the dry spells might actually present a different picture, as shown by these two maps. So in concluding, I would say that the ability to accurately project food security outcomes over a year can help to improve drought response. And interventions that improve resilience and maximize gains in good seasons and minimize losses can be more effectively targeted when we have got these accurate multi-year predictions. And then sub-seasonal rainfall distribution characteristics are also very important and would help to increase the utility of the forecasts. Thank you.
Thank you very much, Tamuka. We'll move on to our next talk here. This talk is by Carly Tozer, and Carly will speak to challenges in learning and application of multi-year forecast in hydropower operations. So the floor is yours.
Thank you. I'll assume I'm sharing my screen okay. So as mentioned, I'm Carly. I work at CSIRO and I'm based down in Tasmania, Australia. So it's morning here for me at the moment. My goal here in presenting today is to introduce you all to a project CSIRO undertook, which focused on the application of multi-year forecasts in hydropower operations in Tasmania, and in particular wanted to speak to our stakeholder engagement efforts, or you might say co-design efforts, and the different experiences, the different outcomes we experienced relative to the different levels of engagement we undertook. So a bit of background about the project. So in 2017, CSIRO embarked on this collaborative research project to explore the utility of multi-year forecasts in Hydro Tasmania's operations. You probably don't know too much about hydro, so Hydro Tasmania operate 30 hydropower stations across 6 water catchments in Tasmania, and these catchments are primarily located in Western Tasmania. So just to confirm that geography here, so we've got mainland Australia and Tasmania is the island state. And so Hydro Tasmania provides electricity to Tasmania, but also exports electricity to mainland Australia via the Basslink cable. And so I've got just this little inset here. So Tasmania is connected to Victoria by this Basslink cable. Hydro Tasmania sells into Australia's national electricity market. And so some, I guess, further context to this project is that in 2015, Basslink actually failed, but this failure occurred at the time that hydro was experiencing quite a prolonged significant drought. And this situation led to an energy security risk to Tasmania. And this situation really highlighted to Hydro Tasmania the need for strategic planning for multi-year climate variations, and so hence our project was born. Oops. Okay, so our initial work plans revolved around CSIRO producing the forecasts, undertaking a skill assessment of relevant variables, primarily rainfall, then CSIRO providing those forecasts with the idea that hydro would then run them through their operational model. Very simple, makes sense. And so I guess, if I was to sort of describe that model in a very lame image, it would just be CSIRO sort of in our little box doing our thing and producing forecasts, providing them to hydro sort of doing their own thing, giving us a little bit of information back. So it was just this kind of back and forth. So what happened, I guess, with this mode of engagement? Seem to have trouble. There we go. So in the first 2 years of the project, we tested different versions of the forecast system, different sets of forecasts, performed skill assessment. We had some good outcomes. We had some skill in climate drivers like ENSO. Still questions around though whether that's relevant for Tasmania. Is an ENSO forecast? Does ENSO actually drive rainfall variability in Tasmania? We did have some patchy skill in rainfall, you know, some skill in long averages, but is a 5-year rainfall average, is that a useful metric for Hydro Tasmania in their operations? We also found we had some skill in temperature. Again, is that useful? So you can see we had some pretty key questions remaining around the Hydro Tasmania's operations, decisions, and the relevant timescales. So it was clear that we, I guess, needed to change things up, and we essentially just needed to speak more to Hydro. And so our next, oh, sorry, just to go back to this model, I guess we in sort of retrospectively looking back at sort of what happened, I'd call this a linear model, and it just really lacked that dual engagement around the problem. So moving forwards, we were fortunate to receive some funding to engage stakeholders in Tasmania in various sectors to speak to the climate decisions that they make and you know, sort of, I guess, the potential utility of climate forecasts in their operations. And Hydro Tasmania was one of those stakeholders. So through this process, we engaged Hydro in a formal interview. And so we had provided a set of questions, and this took them through sort of the decision-making process on various timescales, the risks on various timescales. And this is quite interesting because, you know, despite that we had been engaged with Hydro for a couple of years, it was sort of this process really gave us some new insights. It provided us with the opportunity to meet with new people in the business that we had, you know, never met before. Gave us some new perspectives, which was really useful. You know, we did discover that mainland Australia temperatures are actually relevant because of the connection to the mainland. So, you know, summer heat waves in Melbourne. You know, when people in Melbourne are using their air conditioner, Hydro Tasmania want to take advantage of those price spikes. We also learn a bit more about their scope for using annual to multi-year forecasts. They, you know, run network simulations out several years. They have multi-year storages in their system. And, you know, network maintenance is planned years ahead. You know, they take certain storages offline. And so, you know, example, they don't want some of their storages to be offline during really wet periods because they can't then take advantage of those good conditions for generating electricity. So this was, I guess, the first step in really sort of deepening that engagement with Hydro, and it was really valuable for us. We learned a lot more about their system, and I guess we took it to the next level with the sort of the next project we undertook with them, and that was the development of a toy model of their system, and this was co-designed with Hydro Tasmania, and it really distills this sort of essential components of their system that are relevant to the year-to-year or the multi-year timescale. And this model allowed us to articulate and model how climate information changes their decisions, and allowed us to test whether they can actually derive some benefit by inputting future climate information. So it was sort of, again, really deepening this engagement. So I'll take you through sort of a very crude representation. So just here we've got mainland Australia, sort of state of Victoria in this brown box. We've got the Basslink represented, and Tasmania is your green triangle. So this is, and I've got sort of just an indication of the system there with these storages. We've also got irrigation demands in the system and some environmental demands. There's, you know, fish and aquatic species in the reservoirs that, you know, they require a certain level of the reservoir. So Hydro has to account for that too. And I've also indicated here, so our multi-year storage, the one that we'll be focusing on is this Jing-Jia Great Lake. So the point of this process was to model the role of Jing-Jia Great Lake in the system. So just as an example, I showed before that the key climate influences on the system were rainfall in Western Tasmania, represented here, and then Melbourne temperatures. So as sort of taking us through a scenario, so if the forecast was for a hot summer in Melbourne, well, as I said, everybody will be using their air conditioners, so drawing on the system. So Hydro Tasmania really want to generate electricity to sell into that market to take advantage of the price spike. So that's sort of what's indicated there. And so if that's the forecast ahead, you know, their response today that they would want to bank water in Jing-Jia Great Lakes so they have storage there to use in the future. And then I guess
2 minutes
maybe,
remaining.
thank you. So the opposite end of the scale here is if we've got a dry Western Tasmania. So the goal for them, for hydro, would be reduce the low storage risk. You know, again, we've got to look out for the environmental impacts. So again, their response today would be to bank water in Jing-Jia Great Lake. So for hydro, it really is a trade-off between revenue generation and fulfilling these environmental requirements. So from this modelling process, you know, we found that the environmental improvements can be achieved with minimal change in hydropower revenue when 12-monthly inflow forecasts are considered in operational decisions. So this sort of development of this toy model was really useful and insightful for us. And I guess in regards to this engagement, we found that deep engagement is really critical for deriving any potential use of climate forecast information. But it takes a lot of time, you know, and on both sides, so both the CSIRO side and hydro, you know, we really did have to put a lot of effort to talking to each other, and, you know, commitment on both ends. And in hindsight, sort of, I guess, yeah, looking back on this project, it probably would have been helpful for us to define this level of engagement at the outset. And just to sort of reframe this little image here, is we've kind of more meeting in the middle a bit more with this deeper engagement, and that's been really useful for our project. Thank you.
Thank you very much. If our speakers could re-emerge on our screen, turn their cameras on, and we'll get started with the question and answer. And we also welcome our colleagues online to type in the chat box their questions. We'll begin with a question from Judith Berner, and this is for Jing-Jia. Thanks. Just to follow up, did you find sources of predictability, spatially or temporally, that would not have been captured with dynamical models? In other words, did ML allow you to learn something you would have not anticipated otherwise?
I already put my answer on the message box. Does I need to read it, or I can repeat my?
Yeah, sure. If you could, there's a lot of us here in the room, so we're not all.
Oh, okay. So yes, I think like many kind of machine learning model has can provide kind of a feature map. The feature map is kind of weighting coefficient. So from like at a different lead time, we can look at the feature map of each predictors, like surface temperature or heat content. Then we can for each lead time, we can understand where the precursor is most important. So in this way, we can have some clue, like, oh, so like for like a 12-month lead, so maybe some signal in Indian Ocean or off equatorial area can be important for the forecast in 12 months later. So this can give us kind of an idea to check whether the machine learning model result is consistent with our understanding or not. Sometimes it's not. So in this way, maybe the machine learning result can provide a new clue for understanding. But sometimes the machine learning model can be wrong. So we need to be always be careful on that. So that's my brief answer.
Thanks very much. Question in the room from Jerry Mill.
Yeah, this is for Jing-Jia. Presumably you're looking like at 12-month leads, and you've got a really good training period from observations with a lot of realizations of El Nino events. But have you tried applying this to lead years beyond 2, say out to lead year 2, 3, 4, and 5, when you have much when you're training a period from observations is much more of a challenge. How do you view the prospects for machine learning prediction on these longer time horizons?
You mean the dynamic model has difficulty in forecast answer in like long lead time, and the machine learning can provide a better skill?
No, I'm just talking about what the prospects are for the machine learning technique to make credible predictions for lead years beyond, say, lead year 2.
Oh, okay. Yeah, we did answer forecast up to 12 months. So, but for like multi-year, much longer lead time, we have not yet tried this. Actually, we asked a student to extend the forecast lead time by combining our dynamic model output and machine learning model. So because we use surface temperature and heat content as a predictor, so we say if we can predict the SAT and all the predictors using dynamic model, and then we can use CNN and machine learning model to extend our forecast lead time, right? So, but actually, the result seems not better than the original CNN model. So I'm not quite sure. Maybe it's the source of predictability, internal source of predictability actually limit the lead time of any method. So that's my guess. I'm not quite sure. I cannot answer your question. But if of course we want to predict like multi-year mean, like a decadal prediction is different, and it has different source of predictability, and we can use different data set to training the model, machine learning model, then probably we can do multi-year forecast compare similar to the dynamic model. I think machine learning cannot do any job. There should be strict subject to the intrinsic source of predictability of any predictant. So that's my understanding. I'm not sure it's correct or not. Hello?
Yeah, we'll
Yes?
move on. Thank you
Yeah.
for your answer. Haiyan, if you could ask your question to Tamuka now.
So my first question is for Tamuka. Great talk. Could you please comment on multi-decadal variability and climate change influence on food security in Africa? Do you use climate change information for your policy or decision making at USAID? Thank you.
Much, Haiyan, for that question. So on the subject of multi-decadal variability, I was actually just discussing yesterday with my co-author, Jim Verdin. There has been an observation that in East Africa, because I think we've done studies looking at the range going back as far back as 1900. And these studies done by colleagues at the University of California have identified that in the early part of the 20th century, these droughts, for example, were much less frequent. They were more rare than what we are seeing now. Because, for example, recently we've just seen back-to-back droughts for at least 4 seasons, for March, April, May, as well as October, November, December in East Africa. So this is definitely the climate change aspect is making the droughts a lot more frequent, at least in parts of Africa. As regards the issue of climate change information and how it's used for policy, I'd really like to invite my co-author, Jim Verdin, who is also in the meeting to respond to that, if that's okay.
Yes, climate change information is very important for various aspects of the work of USAID. In the case of the emergency humanitarian work that Tamuka has been speaking about, of course, it's very important to have an understanding of the sort of backdrop to the season-to-season, year-to-year work that is done there, because understanding those trends can help us sort of shade the odds, if you will, in one direction or another, if we understand the way in which certain phenomena might be exacerbating adverse impacts of a standard ENSO event. As it relates to longer term activities, though, development work, there are standing requirements for any development project in USAID that there be upfront climate change vulnerability assessments performed before the investment is made to go into a multi-year development project. So it's definitely on the radar screen for relatively short-term endeavors as well as longer-term development objectives. Over.
This is Antonietta Capotondi. I have a question for Jing-Jia, and it's kind of in the same spirit as what was asked before. But one specific thing that you said is that with the machine learning, you could achieve a better prediction of different type of ENSO relatively to other prediction systems. So I was wondering if you actually looked at the sources of predictability in the cases of different ENSO events.
Yes, thanks, Antonietta. Actually, in the paper, we look at the different source as a feature map for different events like 1997, 98, Big El Nino, and so look at the different feature map for Central Pacific type of El Nino and Eastern Pacific type of El Nino. So actually, the model itself can provide all the feature map for each event. So so at each lead time. So actually, you look at each event at each lead time, the feature map are sometimes different. So that's why sometimes the feature map looks understandable according to our known dynamics, but sometimes it's quite different. So that's it's a very tricky issue. But maybe sometimes it provides a new clue but we needed to better understand, examine whether the feature map information provided in feature map is correct or not. So that's always an issue, and it's always harder to understand the machine learning model output.
Hyan has a question for Carly.
Oh, this is a question for Carly. What environmental variables do you use for your forecast model for hydropower?
So for the model we developed, we were using rainfall and temperature. I know Hydro Tasmania are particularly interested though in sort of these remote climate driver forecasts as well. So ENSO and the IOD. I think one of the challenges, and guess is something still exploring, is the connection, I guess, between these large scale drivers and Tasmanian rainfall variability, for example, is a bit fraught. You know, Tasmania is located sort of in the westerly wind belt, so we can't necessarily take advantage of the sort of predictability in these climate drivers. So that's something we're still exploring, and that's something that Hydro is interested in. But yes, for that particular model, we just used rainfall, looked at using rainfall and temperature forecasts.
Thank you.
This is Rob England Wells with a question for Tamuka. Very interesting and important work you're doing, and I was wondering if you could comment on the extent to, especially with climate change, but already in the context of El Nino, this also starts to become a global consideration where if there's concurrent events in different regions of the world, this stresses the global resources to respond to famine, and like, how much does this global consideration come in as well?
Thank you for that question. It's actually something that we've been observing, and I think actually for for this year. And I can comment more on the, I think the relationship between East Africa and Southern Africa, whereby, you know, for example, with the, this year we had a La Nina. We're just coming out of a season where we had a La Nina, and not typically we associate La Nina with above normal rains in Southern Africa and below normal rains in East Africa. But we had a situation in which actually we had, I guess what you can call a double whammy, in which we had low rainfall, low production in both regions. And I think it's something which probably would stress resources in terms of the responses that are happening. I think as you get more of the crises that are happening around the world, this really tends to stretch the capability of humanitarian actors to be able to supply. And so there's now becomes that need to really prioritize which areas have got a higher need, which and a more pressing need. So I think those are some of the factors. But also there has been an observation that, you know, the El Niños seem to start having stronger impacts with related to climate change as well. And of course, this all plays into the impacts that they have around in different regions around the world. So those are some of the considerations, and I'll leave it again open to Jim if he has got anything that you'd like to add there.
Right. Thank you, Tamuka. Yes, in fact, one of the reasons we're participating in this workshop is because of our keen interest in the potential for multi-year climate forecasts. And one of the motivations is to be able to identify as early as possible the occurrence of synchronous crop failures due to drought in those areas of the world where we have concerns, either because the vulnerable people live there, or the surplus growing area upon which they depend in their region is impacted by drought and has a poor outcome. As Tamuka showed, I mean, having sequential droughts is also very important as well. And the position of USAID is that even though it's a major donor, the resources available are nowhere near enough to meet the needs all around the world. And so it's very, very important that those available resources be applied in a way to get the maximum positive effect. And so we're very concerned about what you describe, and as far as the global food system being disrupted by multiple adverse climatic events, and we hope to work with our science colleagues to develop capabilities that help us see those sorts of events on the horizon as early as possible, so that the word can be sent out not only to humanitarians but to others in a position to do something about it, such as grain traders, insurance companies, finance institutions, etc. Over.
I have one Pedro Dinesio here. One last question for Jing-Jia. Jing-Jia, we know that a lot of the multi-year ENSO predictability comes from predicting multi-year La Nina, that type of sequence, peak of El Nino to 2-year La Nina. Does your AI method can predict other sequences like neutral to El Nino to La Nina or multi-year El Nino? Do you comment more on the sequences that the AI can predict?
Yes, this is a very good question. We didn't, in the paper, we did not check carefully the answers, the predictability of La Nina and El Nino. Maybe the scale should be different according to dynamic model. And we only look at there's actually time series of CNN forecast because the scale is better than dynamic model. I think as far as I remember, the multi-year La Nina can be will forecast. But I did not check carefully the predictability of the ENSO, a different ENSO cycle. So I think this is a very good question. Thank you.
Well, let's once again thank all of our speakers.